So, welcome you all to this lecture of lecture 7, part 1, and we'll discuss transient analysis in this lecture. So, first thing I like to make, first thing I like to, we'll see that what do we exactly mean by transient analysis of circuits. What is a transient here? So circuit analysis can broadly be classified into two parts, that is, one is steady state and another one is transient. So these are the two ways the circuits are analyzed. Steady state means the circuit responses, that is currents and voltages, whatever current and voltages are, these voltages and currents are not time dependent, okay, they are not functions of time, okay. So up to now we have been seeing those resistive circuit mostly with DC circuits. They can be said to be a kind of steady state analysis. The current etc which we found were not actually related to any, they were not actually time dependent, okay. So they are in a way steady state analysis we have been doing, okay. The second way of analyzing circuit is the transient analysis. In this, the responses I's and V's, that the voltages and currents are basically time functions, okay. So that is the difference. That means we have to take consideration of time for having the responses of those circuits. Why should we take considerations of time? We'll just see. If you see this circuit, one of the element which we have been seeing so far is resistance, and resistance can be said to be an instantaneous element. That means if you have a resistance R, and as soon as you connect voltage to it, let me see, there is a switch here, and you just switch on the switch on, that means you connect the resistance to this voltage, the current in the resistance flows rather instantaneously. What do we mean? That means there is no time lag, or there is no time that I is not related to time in any way, okay. Immediately it happens. So resistance is in a way an instantaneous element, and the relation between R and V and I is given by V is equal to IR. This is very simple, which we have already seen. But there are other elements which are not actually that they do not behave in instantaneous manner, okay. So let us see those elements. So those two elements can be said to be a kind of inertial element. They have some kind of inertia in them, and these two elements in electrical engineering are capacitors and inductors. So let us see why capacitor and inductors acts as a inertial element. Let us see capacitance first. In a capacitance, if you see what actually capacitance is. Capacitance is ability of device to hold charges, okay. So that means the charges and in the device, the charges are stored in the device, okay. And how they are stored, that depends on what is the voltage across it. So depending on the voltage across it, the charges it can hold is Q, and this C is called capacitance. So larger is the capacitance, larger is the capacity of that particular capacitance or that particular capacitor to hold the charges. So in a capacitance, this is the basic relation, which is in fact instantaneous, okay. So if you have a capacitor and you know the voltage across it, you immediately also know what is the charges on it, okay, how much charges on there, knowing the capacitance obviously. So this is an instantaneous relation. However, we are interested in what is the relation between V and I in a capacitor, okay, because in electrical engineering we do all the analysis in terms of V and I. So if you see, this Q can be put in a form of I, okay, that is I is dq by dt, all right. And this way the amount of Q deposited on the capacitors depend on the value of I which has flown into it over time, that is from say 0 to t or whatever time it is. So in a capacitor, the amount of charges which has come depends on IDT, that is the integral of IDT. So in this way, if you see in a capacitor, V and I are related in this way, that is the voltage across the capacitor is this integral of IDT into 1 by C, and it's this, if you see this way of seeing the capacitor in terms of voltage and current, then it is no more instantaneous. It actually integrates the amount of current so that you come to know about the voltage, across it. So integration, the current and voltage are not instantaneously related in a capacitor. However, Q may be instantaneously related, but voltage and current would not be instantaneously related. And another way of writing the same equation is I is equal to C dV by dt. Of course, it is actually manifestation of the same equation. So what we found here is, in a capacitor, V and I are not related in instantaneous sense, like a resistance which we saw. And suppose, let us say, we talk about a steady state where the V is not a function of time, or V is constant. In that case, dV by dt would become 0, and in that case I becomes 0. Okay, so in that case, in a steady state, the capacitor would act as an open circuit. We'll see how it acts as an open circuit in a later this one, how a steady state is achieved. But this is how a capacitor is actually behaving. Okay, the another element we'll see now is inductor, and we'll see what is the relation between inductor. In an inductor, if you see, the instantaneous relation is between flux and the current. So this is also instantaneous, but flux and current. Okay, so if current I is flowing, then immediately, instantaneously, there is flux phi associated with it. Okay, and this flux phi, the voltage across any element having phi, is depending on rate of change of flux. Okay, that is d phi by dt, and that comes out to be LdI by dt. So in a inductor, the voltage and current, again, if you see, are related in this way. Either you can say this relation or this relation, both are same. Okay, manifestation of each other. And in a nutshell, I can say V and I again are not related in instantaneous sense. Okay, so there is a time involved, so for I, between I and V, to be related to each other. So time involvement is always there. So the L and C, unlike resistance, are said to be inertial elements. They do not respond to voltage or current immediately in relation to each other. However, in terms of flux and charge, flux in inductor and charge in capacitor are obviously related in instantaneous sense. However, the current and voltages are not related in instantaneous sense. Okay, here also, if we note, in case of a inductor, when a steady state is there, that is di by dt is equal to 0, then if you put it over here, in case of steady state, we'll see how steady state is achieved. That is a different matter. But if this happens and you plug in here, then you find that the voltage across the inductor becomes 0, and thus in a steady state, the inductor will act like a short circuit. Okay, the voltage across it is 0. Okay, so let us try to see what happens in time. Okay, now we are trying to talk about transient analysis. What happens in time when you have a RL and RC circuit? Okay, so we'll just take a smaller circuit first, that is one RL circuit, one R and L connected to a voltage source, and then we'll write the circuit equation. Remember, KVL and KCL are applicable to all kinds of circuits: linear, non-linear, instantaneous, transient, whatever you call. Okay, so here I'm trying to write circuit equation for this particular circuit. There is a voltage source, a resistance, and inductance. Okay, so if I am writing a mesh equation for this, then I can write V minus IR. So I have taken this direction, minus IR minus VL, opposition this the voltage across this is in opposition to the current, and that is how you get KVL equation. And this VL can be put as LdI by dt, as we have seen in the earlier slide, and this is how the equation is for a RL circuit. Okay, so this is a equation for RL circuit, and if you see, this is basically a differential equation, and to be more precise, it is in fact first order differential equation. Order is 1. Okay, now we'll talk about RC circuit. Again, in a similar way, if you see, you have a V, a resistance and a capacitor, and V is equal to IR and VC. In the same way, you can write the equation as we did for this one, that is the KVL, and you can then put VC is integral I dt, then you again get a this kind of equation, which is obviously having some kind of time variable. Okay, you can also write the bottom equation in slightly different way. You can, instead of putting VC is equal to I dt, I can also put I is equal to C dVC by dt, and by that also I can get a different, this is also a differential equation, that is just to show that this you get RC dVC by dt minus VC equal to 0. So this is what you have, a first order differential equation again for a RC circuit, which is almost similar to this one. Okay, if you see, both are almost similar, and this is also called a differential equation, though it is integral equation and you can always differentiate to get a differential equation. So again, a first order differential equation. Okay, so different ways of writing the same circuit, but the idea here is, when you write the equations, there is a the variable of time that comes into play, and then you say that these equations will have to be solved, to this differential equations have to be solved to find the relation between V and I. So similar extension, if I have a voltage source and a resistance, an inductor and a capacitance, now there are 3 elements, and then if you see, you can put all these 3 element KVL for 3 element, and these are the 3 elements, and accordingly you can put VL, VC and I dt and replace them in this. Again, you get a differential equation. This would be a second order differential equation. So this is how we analyze transient circuit, by writing its equation, KVL equations, and finding the voltage and current by solving these differential equations. Okay, now as of now, we have been, whatever circuits we saw, we didn't talk about where the time actually comes in. Okay, because the circuit is, this voltage source is always there according to this circuit. Okay, so for getting the notion of time into our problem, now what I am doing is I am making a circuit in a slightly different way. Here again you have a RL circuit, but there is also a switch over here. Okay, S, and now I am trying to have a notion of time. That means at the closure of this switch, you get RLN connected to a voltage source, and that makes starting of time in the circuit. So that is t equal to 0 when the closed switch is closed. So if you see here, this is corresponding to this circuit. Okay, so this is at t equal to 0, this kind of circuit you get. Okay, so now you also have a meaning of time as far as this particular problem is concerned. And again, I am writing the equation which you have already done. Same equation will be written. Okay, but here we now know what is time, and this is the differential equation which we also saw earlier, and solution of that differential equation come about to be this. We'll see how to solve them later on, but Let us assume that we know how to solve it, and this is the solution you get, because this is a differential equation, first order differential equation, and its solution comes like this, the way it is shown. Okay, I is equal to V by R 1 minus e raised to power minus R by L into T. This is the current. Okay, so after solving for I, the differential equation, we'll see how to solve it in a later lectures, but let us assume for now, because that will rather than going into the mathematics, we remain in with the circuit at this time. So this is how you get I, and if you want to plot this I, of course it is function of time now. Okay, so this is time function, and at t equal to 0, when you put at t equal to 0, this becomes 1, this becomes 1, so I equal to 0. So I starts with 0. Obviously, you can just note into the circuit in intuitive sense also, when this was not connected, just before t equal to 0, there was no current flowing into it because switch was open. And as soon as you put the switch on, it doesn't mean that the current will rush immediately. It has to start from the same place, that is from 0. And that is why some people say the current in inductor cannot change instantaneously. Okay, so it starts from 0 and then it rises up to value V by R. At t, as t tends to infinity, you will see that this part becomes 0, and I finally comes to V by R. That means up to this point. Okay, so at t equal to infinity, we know that it is going to be V by R, and in between there is a rise in this manner. Okay, so I can say that this is response of the circuit. That a response means current or voltages in time domain. So that is how the circuit behaves. Okay, now two important questions we can answer. When the circuit is in transient state, when we say that the circuit, we are doing a transient analysis, I told you we'll say when I depends on time, and when we say it is in steady state, when I doesn't depend on time. Okay, so let us check. So if you see this, up to some point, this I has definite relation with t. Okay, but after certain amount of time, here there is no relation with t. The time, the I becomes constant. So I can say that at this point, in this range, the circuit has come to a steady state, whereas in this range, the circuit is in transient state. Okay, now how do I tell in case of time? If somebody says up to what time you say that the circuit is in transient state, and up to what time you say now it is in steady state? For that, I have to know how it rises. Okay, if it rises very fast, then this steady state is reached very early. If it rises very slowly, then steady state may reach after very much amount of time. Okay, so I can say that this is not defined just by saying infinite time or zero time, but we can say that it depends upon the time constants of a circuit. We'll talk about time constant in later thing, but what I want to say, time constant means it decides how inertial your circuit is, how much time it takes to reach the steady state. If it takes lot of time, the circuit is slow, sluggish, that means something like this, then we say the time constant of the circuit is large. Okay, normally it is given by tau, so tau is large. If it reaches very fast, okay, it is very fast, then you say that tau is small. And normally we say after 5 taus, effectively the circuit has come to a steady state. So this tau actually defines up to what point the circuit is said to be in steady state, and up to what point the circuit would be in transient state. So we'll stop here for now, and in the next lecture we will see how to further analyze the circuits, and we'll also talk about time constant and solution of all the equations which we saw here. So I'll stop here.